Thank you, Aparna, and thanks for NEX for this great opportunity to present about the research for 3D printing of concrete and polymer concrete. So basically, in my presentation, I will discuss part of the work I have done under a grant funded by the National Science Foundation, and it was already published recently last spring on an ACI special publication. Basically, we teamed academia and industry with a Raleigh-based startup company to produce 3D printed concrete and polymer concrete coral reefs to fight shoreline erosion. Just a little bit of introduction to the size of the problem. We're here located in the state of North Carolina. We do have extensive shoreline, and there is a huge acreage of land being lost every year due to erosion, and this is a massive devastation to to real estate, to tourism, to the environment in general, even to the highway industry, because a lot of these property or a lot of these land damaged passes across extensive highway network. So in this presentation, I'll talk in general about erosion or scour. I'll present the problem and the mega size problem that we're facing right now. I'll list the objectives of our research, and basically I'll show a kind of how trade off with current solutions, what current solutions are there in the market, and how the 3D printing of concrete and polymer concrete is presenting a very economic and user-friendly alternative. Finally, I'll speak about the technology which is patented for the startup company we work with, and what we did for the mix development and the advantages of our work. So first thing, as we all know about scour, it's simply it's a wave action on beaches, and usually it increases around breakwaters or along cliffs. When water is channeled by those structures, it creates a faster flow, and that expedites the rate of erosion, specifically if we have sandy beaches. Part of that, we do have tidal scour, which is seafloor erosion, and that's usually developed when we have strong tidal currents resulting from the removal of the sediments within in the inshore, and the formation of deep holes and channels. That scour is being affected by multiple parameters which can either enhance or mitigate its effect. First, the geometry of the channels, the dynamic properties of the flow, I mean here the water flow within the stream or the sea or the ocean, the soil bed conditions, and whether there is scour mitigation techniques or the lack of scour mitigation techniques, as in a lot of the mileage across our shorelines within the United States, and especially in the state of North Carolina. So that creates a mega problem for us. According to the National Oceanographic Services, the United States shoreline, it extends for more than 150,000 kilometers, or like 95,000 plus miles. And all, as I stated earlier in this presentation in the previous couple slides, the erosion is resulting in massive losses of land, and that's prime locations, beachfront locations, property destruction. Definitely there is a negative impact in tourism and, a troubled marine life, and a lot of these results in litigation or increased insurance claims. We all have seen, the last two hurricanes over the past 15 days. One has, bombarded Florida. Actually, both have bombarded Florida, and one was extended to the western side of the state of North Carolina. And we're having a massive problem with insurance, and probably a lot of court cases are gonna be there. So the parties or the stakeholders who are benefiting from this research, because they are the massively devastated, that includes all the investors in the real estate business, owners of beachfront properties, insurance companies, government agency. One of them is the North Carolina DOT that we're trying to do some work to enhance the resilience of the infrastructure, mainly all the roadways close to the shoreline, and then definitely tourism industry as well. So if we try to put some numbers or figures for these losses in the United States, we're having 500 million losses per year just for the properties lost. 80,000 acres of coastal wetlands are lost per year. This is equivalent to, if you think of a football field, 7 of them are disappearing every hour across the year. So you can think about the massive acreage being lost to scour or shoreline erosion. But over the 10 years, or almost 10-year period between 1998 and 2009, the U.S. lost a total wetland area that is greater than the state of Rhode Island. Just think about losing 25 feet every year of the coastal line along the whole length of the 150,000 kilometers. That can tell you the massive devastation due to this recession of the coastal lines. And think about the crowd losing their lives, their property, their investment, etc., due to these losses. Now, what we're trying to accomplish using our research is to provide an alternative erosion mitigation solution to all these affected parties. And based on a research that we did, and more than 500 stakeholder questioned and surveyed along the 50 states and some locations over the world for countries with massive erosion problems, we were kind of told that the main proposal or the value proposition that we should have would include a 25-year plus solution, because all the current solutions are not that permanent. Basically, we're looking about economic, as Dr. Taha said on the previous presentation, we have to think about life cycle cost, not the immediate materials cost, and definitely had to match the new trend on the international arena of being environmentally accepted and approved by governments and municipalities. At the end, we need our solution to have a minimal need for MR&R, maintenance, repair, and replacement. Before I mention what we have done on 3D printing research and how it is applied, I would like to touch on the current solutions and how we're fighting this problem aside of the alternative we're presenting in this research. Here in the state of North Carolina and a lot of the other states, we have surveyed all the beachfront locations have shifted to non-structural techniques because the construction of bulkheads or riprapping or using concrete walls is not approved by the states or cities or municipalities. There is legal issues against this. So jumping to the non-structural solution, we find that beach nourishment is a major technology through the dredging and bringing similar sand, usually from a lot deeper area on the ocean or the sea, to the shore to kind of nourish and provide a buffer against scour. There has been more than 2,000 large projects that was done over the past 100 years within the United States. However, a lot of this is not very efficient because the new sand is also being washed into the sea. It's also very labor intensive and it's temporary. It lasts for 5 to 8 years and it's very costly. Other solutions, and these are the structural ones, and like here in the state of North Carolina, a lot of the locations, they ban this use, but we can either use breakwater to dissipate the wave energy use bulkheads, or rip wrapping. These are probably a stronger solution and a little bit more permanent than the beach nourishment using dredging. However, as I just mentioned, they are kind of banned in many locations. Finally, there is a nature imitation, which is the use of living shorelines. Basically, some plants, including mangroves, they do have their deeply rooted portion, which kind of stitches the soil and provide enhanced shear capacity, and that basically enables the soil to resist sliding due to the wave, force or the tidal movement, and that basically dramatically mitigates the impact of the scour or erosion. Finally, shoreline sloping and using some sort of fabric to support the soils, and that depends basically on the bearing and the shear force between the aggregates. Traditionally, larger diameter particles could be used on a steeper slope as compared to smaller grain particles like sand and silt. Basically, this is some sort of wrap up. And this slide, it shows like the use of vegetation, edging, sills, breakwaters, revetment or bulkheads, and that, the left-hand side, that is the greener, softer technology, living shorelines. The right side is the harder technology, which could be a little bit more permanent. But again, think about the cost. And when we talk about harder technologies, there is a major ban from some governments along the United States, and they're prohibited. So basically, all the current techniques I listed are expensive. Some of the research that we made included the surveying, property management, hotel owners, tourism, personnel, and we came to an average conclusion around the United States that a 1 mile nourishment could cost up to $6 million US for a lifespan of no longer than 8 years. Sometimes it could be as little as 6 years in some of the locations here in the Outer Banks in North Carolina. Now, whenever we come to the hard shore lines, not the dredging or the nourishment, we can see that some of the states are not approving them per se. Bulkheads are increasing the erosion at the toe of the structure. They could cause adverse effect to the ecological system. And whenever timber shoreline hardening are used, there is negative leaching impact on the industry. The use of concrete tripods are not scenic, and there is a general harm to the tourism industry. Shoreline sloping could be a little better. However, whenever there is flooding, as we've seen over the past few weeks, or high tides, it will definitely be inefficient. Now to the use or the incorporation of our technology using the 3D printing of concrete to provide a solution for this problem. We have proposed a non-traditional 3D printing technology, which is basically dependent on the dry forming or the use of dry beds, where we do have, as you see on the picture, some sort of a container that is loaded with the dry constituents, and that could include cement. It could include any sort of supplementary cementitious material in partial replacement of cement, or as Dr. Taha said on the previous presentation, we're having some polymer replacement. So it's not a polymer concrete or polymer impregnated, but we're having some sort of partial replacement of cement with polymers up to 20-25%. And once we have this on the dry bed, we kind of embed the liquid, or the hydration process starts by dipping this network or the grid of that seeming to be like small pipes or straws, and that is controlled by a software that tells how deep each of these pipes would go and the rate of infusion of water, and that results into localized hardening of the cement, or the cement and the polymer to form a shape that is as close as possible to coral reefs. I'll elaborate more when it comes to a case study in the next few slides. So basically, on the research, we did some mixed development for dry forming. Here we're having a little bit of challenges. First of all, how far could we go, or what's the distance in the X and Y direction between the straws where the infusion of water would not or would still be efficient. We don't want the water from two consecutive tubes to overlap, otherwise it will be overhydrated, or we don't want this pipes to be so far away, otherwise there will be massive unhydrated portions, and definitely that will lead into the collapse of the formed body, or the 3D printed body, which is the 3D printed coral reefs. So in order to fix this, we first thought about the mixed design, and we tried our best so that we can arrive to a minimal compressive strength of 2,500 to 3,000 psi, and the water injection rate has to average anywhere between 0.19 or 0.2 to 0.24 water to cementitious material, and this is a ratio by weight. We formed first smaller samples. As you see, it's 2 inch by 2 inch cubes, and we used one needle water injection. So basically, because of the distance here, if you inject at the center, it will be a 1 inch each way. And what we did is we found that up to 2 hours there has been a collapse. So basically, these are the shapes of the cubes after being removed within 2 hours, and this is kind of unacceptable because whenever this will be implemented on the bigger scale dry bed, we would like to have a faster rate of hardening. Otherwise, the productivity rates of the printer will slow down. So in order to fix this problem, we shifted to larger cylinders, that is 3 inch by 6 inch, and we tried to inject different percentages of chemicals, basically accelerators for setting. And we have done, here you see 2% accelerators, 4% accelerators, and basically the 4% accelerators up till 3 hours, it started to show some work where we could detach the cylinder, which again, this is a 3 by 6. So whenever we inject with one needle, the distance around it, it will be a 1.5 inch to each end of the cylinder. So a strength of 200 psi was attained on the first 3 hours, which was deemed acceptable by given the productivity rate that the company was looking for. At this level, again, what we did, we kept repeating until we guaranteed that the injection at this rate, the water cementitious material, and at the percent of 4% accelerator could be used at a 3 hour time rate. And pouring could once we pour and inject our fluid, then in 3 hours we can start removing the printer, and we can generate a full-sized coral reef block. As you can see here, the 3D printing procedure, it started by collecting some random full-scale coral reefs pictures to be entered to or generated by our software that controls the machine, and basically it tells us how long or how deep do we need to dig our printing needles or these small straws or pipelines. So here basically, if you look at this, then definitely there is extended dipping for the needle all the way down, and here you can see that it's not going as deeper. So basically here that shows a picture of how the injection is distributed along the dry bed of our cementitious material, or the cement and the supplementary cementitious material, or the cement plus polymers, before dipping our straws. So this is basically the procedure. This is a dry bed, the straws being dipped in, and then this generates this type of shape, and this is loaded on trucks, and basically it is thrown at shallow water. So that, again, it's not considered a living shoreline, but by the government here in the state of North Carolina, this is not a dead or a hard shoreline reinforcement as bulkheads or ripraps or tripods. So it is basically acceptable if being used on a shallow waters. So it is considered as a regular or as an enhancement for the natural coral reefs, which is suffering of coral bleaching due to wrong practices, due to fishing and wrong, the people poor practice within our shorelines. So this dry bed 3D printing of concrete coral reefs kind of provide a permanent solution, given that we cannot justify or judge, but the expected lifespan is going to extend way beyond 25 years as compared to 6 to 8 years of nourishment. And during this time, no maintenance will be required. It's sort of green and sustainable, given that we can lower the carbon footprint depending on the reduction of cement or the use of different supplementary cementitious materials in lieu of cement, or using recycled materials. The hardened shoreline cost using this technology is calculated at a 0.9 million. It's less than 1 million compared to 6 to 8 million for beach nourishment or sand nourishment. And again, consider the life cycle cost. When we talk about nourishment, we're considering no more than 8 years versus up to or more than 25 years for this technology. Just to take this one step further, we're currently working on a newer research to update the mix, not the technology. The technology has been validated, and using this dry bed technique for 3D printing of coral reefs is already there, and there are a couple projects in the Florida area and down by Texas as well. But what we're trying to accomplish is to modify our concrete mix to be as environmentally friendly as possible. So we started using calcined clay, or calcination of clay dredged, from our own water beds. So this on the right side, the top picture, this is dredged clay material that was obtained from waterway on the state of Virginia, and it was transported to North Carolina. And then the lower side here, that is the picture of a calcined clay. It was calcinated in an indirect rotary calciner at a temperature of 750 to 800 degrees Celsius, which is anywhere from 13 to 1500 Fahrenheit. And then the rate of calcination or feeding the calciner was 20 pounds of the material per hour, and the duration was a 45-minute for calcination. Now this calcined clay, after being obtained, was used in partial replacement of cement. Again, the technology is validated, the rate of water infusion is validated, but we're trying here to cut down on the amount of cement. So we have done multiple mixes using a control specimen with no calcine clay, and then we did different mixes using 10%, 20%, and 30% calcination or calcine clay. Here, as you can see, up to actually 40%, almost 40% here. And we have done, compressive strength testing for, the control specimen, and for all the mixes up to 40% calcine clay. And we're here showing how the strength is looking at, days 1, 3, 7, 14, and 28. So we can see that there is acceptable rate, specifically if we talk about 20 to 30% calcination, the amount of effect on the strength is really minimal. Looking at this, it's less than probably 5% reduction, or even not that. Just to ensure how effective the calcination is, we tried the mixes, again, the control mix and other mixes, using no calcination. So basically just reduced cement weight and no calcine clay. And just, we wanted to make sure that the calcination has, or the calcine clay is having a literally good effect. And we can see here at days 1 through day 7 that we're having a dramatical decrease on the strength. So if you compare this 40% or this 30 or 20% even without calcine clay and reduced cement versus calcine clay and reduced cement, we have seen significant impact of the calcination or the calcine clay, showing a very promising contribution of this calcine clay on the strength of concrete. And think about 20 to 30% reduction of cement. We all know that a ton of cement result in almost a ton of CO2 to the environment. So think about, the massive distances that could be fortified using calcine clay in partial replacement of cement in 3D printing of concrete, and that would definitely, add up to multi-million tons of carbon dioxide being saved from emission to the environment. In conclusion, we have seen that the dredged clay material calcined using the technology of the indirect rotary calciner and the temperature ranging from 13 to 1500 degrees Fahrenheit displayed sufficient pozzolanic activity. Thus, the calcine clay could basically be very successfully used in the development of concrete mixes with lower cement content and reduced carbon footprint, which is good for the environment. Optimum range suggested is 20% of cement replacement, which basically results in a similar or a very high 28-day final compressive strength. And that 20%, considering how much concrete we're using and how much cement we're going to save, will basically result in a significant carbon footprint reduction. So these are the pages from the publications that we have for shoreline resilience through advanced manufacturing. This is for ACI Materials Journal. And then on the ASC held on, this one is for the dry bed technology and using the Type M mortar. Then the new research about calcine clay was published in a journal, in a conference proceeding on the ASC in the Auburn, the 60th annual Associated Schools of Construction ASC conference in Auburn University last April. So with this, I conclude my presentation. I hope I have done it in time, and I do welcome questions. Thank you.
Dr. Akhnoukh, thank you so much for your presentation. Yeah, it was wonderful to learn about coral reef and 3D printing together. And also you tackle a very important problem of erosion, which is very, it's easily forgotten thing, but it's important. So
Yeah.
uh, I'm just looking at the questions. I would ask the participants, if you have any questions, please share with us.
Do you think they can ask in voice if they want to have a discussion, or you don't do
Uh,
that?
yeah, I don't think they have that permission. Uh, they are muted. They are attendees with, like, they are muted.
Oh, is that right?
Yeah, they cannot unmute themselves.
I tried to unmute myself when Dr. Taha was explaining, and I wanted to ask a question, but did you get to hear my voice at that time or not?
No, we didn't hear you.
Oh, okay.
Okay, so I'm just looking at the questions.
Yeah, the reason I said if somebody wants to ask, because sometimes a question could generate into a discussion, and I personally learn from the discussion. So,
Yeah,
like,
no, sure.
instead of being like a one-way, a question asked, and I keep, elaborating on the answer without getting a feedback from the person who made the question. So, but anyway,
Yeah, one of the question which we have here is, so what was the application of this coral reef? Was it actual implemented in any place?
yes, it is implemented in two states. One of them is in Florida, and the other one in Texas. The company I was talking to them that I do research with, they just got even a contract up in Virginia and another one in Louisiana to implement the same technology there. And these are full-blown projects for several miles of shoreline protection. At the state of North Carolina, here we got we had a small pilot project on the Outer Banks in Mantheo, where we have Coastal Studies Institute (CSI), which is a small research unit for the East Carolina University, and we're trying like a small pilot project there, but it's not like a commercial scale yet at the state of North Carolina.
Okay, great. Great. So that's interesting. So this is already implemented.
Yes, it
Mhm.
is. I mean, it's about 3 years now of work, or
Mhm.
4 years of work, and we started to see commercial projects over the past 12 months, maybe.
Our next question is, so when you talk about coral reef
Mhm.
under the water, so how is the durability and other checks done?
How about, sorry, the
How,
durability?
yeah, the durability and other checks done. I
Yeah,
maybe I think the conventional when they say other checks, I think they are related to maybe what we do for the conventional concrete, I guess. Yeah.
yes, primarily we're doing testing for compressive strengths and the two moduli, the modulus of elasticity and modulus of rupture. We've not done any further any more long term, what else would we expect? I mean, there is no freeze thaw. There is definitely no alkali silica reactivity given the type of supplementary cementitious material and the percentage we're using. So it's more of compressive strength, modulus of rupture, modulus of elasticity, and results are very comparable to conventional concrete. And presumably, this would be okay if we're using this in tripods and so. So it is similar to concrete structures. The difference, it is randomly shaped as coral reefs, and that it can be used in shallow waters. So it doesn't hurt the environment. It doesn't hurt the tourism industry as well.
Yeah, great. Yeah, I think I do agree with your response. So going with next, um, yeah, going with next question, we have is you mentioned about recycled materials. Have
Uh-huh.
you included in your design, and how those can be included if someone wants to uh, get in touch with using these into 3D printing?
Okay, we're currently trying to use blast furnace slag. I mean, this is something we're trying to use in addition to the calcined clay. We've used type F fly ash as well. Basically, these are the recycled materials we are using in this research. The results are not out yet, but we're seeing some good potential for you know, uh, for more implementation or more consideration of different types of recycled materials. Now, I do welcome any contact if any supplier, any person have suggestions or materials to provide. I mean, definitely, my contacts are available, and I do welcome doing further research to incorporate any materials on this project.
Okay, great. Yeah, thank you. And our last question is uh, regarding the mixed design.
Uh-huh.
Uh, the mixed design which are presented in the presentation, uh, were were those the same used for the field application?
Yes, yes, they are. The ones that I presented, the first ones using the mortar is the ones that are used on the older two projects, the one in Texas and the one in Florida. Now, the last project we landed recently in Virginia, we're trying there to incorporate the calcined clay. As I mentioned, we just published this on last April, so it is like 5, 6 months old. And this is what we are trying to use in our newest project. And I mean, I think it will be, there, and I think going from there depends on where we are in the nation and depends on the availability of this source of clay to be calcined. It will be a better option given the fact that we can cut down the 20% of cement quantity on the production of the coral reefs.
Okay, yeah, that's great. So yeah, we have one more question.
Uh-huh.
So as you spoke about reducing the cement content to 20%, and also there were some results for 40%.
Uh-huh.
So what are the possibilities of using, like further reducing the cement content to get better mixed design without losing compressive strength? Is there any study?
Yes, this is a great question, actually. I shifted to fully to no cement or zero cement using geopolymers. We used granulated blast furnace slag and type F fly ash, and we activated that by these were precursors, and we used activators like sodium silicates and sodium hydroxide.
Hmm.
The problem we faced, well, initial cost is not little. Again, as Dr. Taha mentioned on the previous uh, presentation, we have to think on a longer term and life cycle costs, yet this is not digested by the clients. That's one thing. Also, working with geopolymers, we found that results are highly dependent on the quality of the type F ash or the furnace slag. So we see whenever we do compression or modulus testing, there is a high variability dependent on the source. So data are not 100% reliable, but the short answer is yes. We're considering cutting cement up to 100% cutting or 0% use of cement to have a pure geopolymer concrete.
Yeah, that would be a great solution.
Yeah, NEX would be happy, I know, but now whether the whether the customers will be willing to buy into that immediately, or we need to provide some, I don't know whether there
Yeah,
will
I
be
mean,
some.
for any new technology, it takes time for
Definitely,
consumers to get.
definitely. To be
Yeah,
introduced, it's not an
yeah,
easy task,
yeah.
especially that here the technology is on the material and on the way we're doing the 3D printing together. So it's kind of
Yeah,
revolutionary.
yeah, yeah. Both were new fields to apply. Yeah.
Yes.
Great. Thank you so much, Dr. Akhnoukh, for
No
your
problem.
presentation, and it was wonderful. You tackled the questions very well, and you answered them to the satisfaction of all our audience. Thank you so much.
Yeah, thanks, Aparna. I really appreciate what ACI and Next are doing to disseminate this knowledge and bringing, a lot of the industry practitioners and academicians together. It's a great initiative. I truly appreciate it.